Hello everyone, and welcome to another video in a series of videos in which we are looking at different types of analyses and how you can execute those analyses in the program SPSS. So in the last videos, we were looking at linear regression and how you execute linear regression in SPSS. And in the latest video, we looked at the basic principles of another type of regression analysis, specifically logistic regression analysis. So in this video, obviously, we will be looking at how you can execute logistic regression in SPSS. Now, remember that in the last video that we discussed, logistic regression is a type of regression analysis that is very closely related to linear regression. The big difference is that we use it when we have a dichotomized dependent variable. So when our outcome can only take two different values, usually 0 or 1. So to illustrate how logistic regression works, I'm going to use this data set called infarction.sav, in which we have data that is derived from a case control study in which different types of variables were analyzed in relation to having an infarction, yes or no, which is a dichotomized outcome. And I will do three types of regression analysis, one with a dichotomized independent variable, a categorical independent variable, and a continuous independent variable. So without further ado, let's get right into it. So to employ a logistic regression analysis, we're going to analyze, we will go to regression, binary logistic, and we will get a similar pop-up screen as we saw with linear regression. So a lot of things are similar, some are not, but for instance, we still have an input field for a dependent variable. So remember, our dependent variable in the case of a logistic regression is a dichotomized variable. In our case, it's whether or not a patient has got an infarction, yes or no. And we also have a block called covariates. So in covariates, we are going to put all of our independent variables. In our case, we're going to do three separate univariate logistic regressions, meaning that it's one independent variable at a time. So in this case, let's look at the relationship between smoking, yes or no, and an infarction, yes or no. So there's a couple of things that you can select when you want to execute the logistic regression. In this case, I'm going to go to options to get the 95% confidence intervals. That is the only thing that I will do at this point. So let's press OK. Obviously, you can also write this to your syntax if you want, but in our case, we're just going to look straight at the output. So just like with linear regression, we're going to get a whole slew of outputs. So let's go through it step by step. Some of the tables I will skip because they're irrelevant at this point, but let's see how far we can get. So in the first table, we can see which of our cases, which of our data points are included in our analysis. So in this case, what we can see is that from the in total 420 cases, observations in our data set, all of them have been included. 0 of the cases are missing. So on both the outcome and the independent variable, we have data available. In the second table here, the dependent variable coding, we see what is the dependent variable coding. In this case, we can see which outcome is coded as 0 and which outcome is coded as 1. It's good to know that when you do logistic regression analysis, typically the logistic regression will calculate the regression based on what is coded as 1. So it will calculate the oddses and odds ratios for the value that is coded as 1. So in this case, when we start interpreting our model, everything will be calculated for the patient being 1. So for the people that have an infarction. So the next table is the classification table. I will cover this one in the next video because it's going to be used to judge the quality of our logistic model, which is something beyond the scope of this particular video. In these two tables, we see the results for our model in which no variables are included. So we are also going to skip over those. And that's where the interesting stuff starts to happen. Block 1, where we are first greeted by the table called omnibus test for model coefficients and the model summary. So the table with the omnibus test of model coefficients is actually the log likelihood ratio. Now remember, the log likelihood ratio was the difference in -2 log likelihood, which we can see here, between the model that we estimated with our independent variable and the model in which no variables were included. So in this case, the -2 log likelihood that is reported here is the value for the -2 log likelihood of our model that includes our independent variable. Subsequently, this difference in log likelihoods shows us the difference between this -2 log likelihood and the -2 log likelihood for a model that does not include any variables. It is not reported, but if you really want to, you can of course calculate it by just adding these two values up. So we can see that the log likelihood ratio in this case has a value of 11.052. Follows 1 degree of freedom and has a significance level of 0.01. So that means that our model improves significantly using our independent variable smoking. So it seems that our variable smoking is provides a significantly better model than a model in which we did not incorporate smoking. Now, once again, we have the classification table, but for now I'll skip over that. So make sure that if you want to know how that works, go to the next video in this series. And then we will be greeted by the very last table, which is actually the table that we are most often interested in, which is the variables in the equation, which shows us the regression equation. In this case, it's very similar to what we saw with linear regression, but there's a couple of things that are different. First of all, note that the constant of the regression equation is reported in the very bottom row in this case. For linear regression, for some reason, this is always reported in the most upper row of the analysis. In this case, for logistic regression, it's on the bottom. So we can see that our B0, the intercept or the constant, has a value of -0.171. Now remember, the constant gave us the value for the outcome when the independent variable is 0. So in this case, that means that those are the estimated log odds on an infarction for those that do not smoke. Because in this case, smokers are coded as 1 and non-smokers are coded as 0. So when we fill in 0 for our smoking coefficient, the only thing that we're left with is the constant. So those are the estimated log odds on an infarction for those who do not smoke. -0.171. In the row above that, we see the row for our beta-1 coefficient, so the regression coefficient. And remember, the regression coefficient shows us the difference in outcome, the estimated difference in outcome for 1 unit increase in our independent variable. Now in this case, the only value that our independent variable can take besides 0 is 1, because somebody does smoke or somebody does not smoke. So in this case, this gives us the estimated difference in log odds on an infarction for smokers compared to non-smokers. Remember, it's a contrast in this case, so the difference in log odds between smokers and non-smokers. Now remember that in the last video, we were talking about that those log odds aren't very intuitive. How do we really interpret those? It's kind of difficult. So what we usually do is we take the exponent of these log odds, and that gives us the exponent b. And in this case, that is a new column that's added to this regression equation that we did not see in linear regression because we did not use log odds there. So what we can see here on the bottom now is that we have an exponent b of 0.843. Now remember, because we transformed a log odds into odds, this interprets as follows now. The odds on an infarction for a non-smoker are 0.843. Not in contrast to anything, just the odds for a non-smoker on an infarction are 0.843. Now, the interpretation for the beta-1 coefficient, we see that we have an exponent b of 2.225. What does that mean? Well, remember, the 0.8, which is the thing that we are exponentiating, is a difference in log odds between smokers and non-smokers. So when we exponentiate that value, we will get a ratio between two odds in this case. So how do we interpret this? Well, the odds for on an infarction for smokers is 2.225 times larger than for people that do not smoke. So in this case, it's a multiplicative interpretation because we are now on a ratio scale. And also because we transformed a difference in log odds, we get a ratio between odds in this case. So when we look closer to the rest of the table, a lot of similarities arise between linear regression and logistic regression. For instance, we see we have a standard error that's similar to what we saw in linear regression. We see we have a significance level, we have degrees of freedom, and we also have a confidence interval around the exponent b. The only thing that's a bit different is that instead of a column with t, because remember we tested our coefficient using the t distribution, in this case we don't use the t distribution, but we use the Wald distribution. I won't get into what exactly that means, but what you need to know is that the Wald statistics is calculated by dividing the regression coefficient by the standard error and squaring that result. In this case, that gives us a Wald statistic of 10.625. And a Wald statistics follows approximately a chi-square distribution with some amount of degrees of freedom. In this case, just 1. And as you know, with a chi-square distributed test statistic and an amount of degrees of freedom, we can find a p-value. In this case, that is 0.01. And if you've been paying attention, you can see that that closely relates to what we saw with the log likelihood ratio. It's the same p-value, or almost the same p-value. And we can see that the test statistics are also fairly similar. They're not the same, but they're almost similar. In this case, we draw the same conclusion with both test results. That doesn't always have to be the case, but in this case, the result of both tests is the same. Finally, we can also draw that same conclusion by looking at the confidence interval. How do we do that? Well, we can see that the value for 1, which would indicate that there is no effect, because remember, a 1 on a ratio scale means that the ratio between the two values is the same, so no effect, is not incorporated in this confidence interval. It does not overlap with 1. In that case, we can also reject the null hypothesis, in this case, that there is no effect, because 1 falls outside of that interval. So it gives you, once again, the same conclusion, but based on a different test. Okay, so now that we've covered the logistic regression for a dichotomized independent variable, let's take a look at how it looks when we use a categorical variable, so one that has multiple categories. We can go to Analyze, we can go back to Binary Logistic. We take out smoking in this case, and what we'll do is we will use the variable for BMI. Now, as you can see, BMI is originally a continuous variable, and we're going to use that in a bit to show you how that works. But in this case, I want to look at the categorical variable for BMI first, one that I created based on percentiles. So I took BMI and I divided it into 6 equal groups based on sample size. So we will enter the variable, but before we press on, we have to tell SPSS that we want to make dummy variables out of this categorical variable. Now, how dummies work, I will also explain in another video. But what it boils down to is that when we do not indicate that this is a categorical variable, what SPSS will do is just by default treat it as a continuous variable. And that is, of course, not really possible in this case. I mean, technically it is possible, but it will not yield correct results. So what we'll do is naturally we'll go to the button categorical, and then we'll get a new screen. In this screen, we will have to indicate which particular covariates are actually categorical variables. So in this case, we just have 1. We drag it over to the other screen. And then what we can do is we can choose whether we want to have the first category of the categorical variable as our reference category or the last category as our reference category. So in this case, I will take the first as our reference category. Make sure you press first and then click change, and you'll see that it switches to first. That's important. Press continue, and we're just going to run the analysis again. Once again, we will be greeted with a bunch of output. And in this case, what we can see is that apparently on BMI, there are some missing values because not every one of the 420 cases has been included. We can see that 5 cases are missing, which yields a total of 415 included cases in our analysis. Now, we can see the dependent coding variables, but those haven't changed because we're still using the same outcome. Now, since we are using a categorical variable, we will get a variable coding table. So in this case, not just for our dependent variable, but also for our independent variable. And that's because we're using dummies. So for each category, we are making a kind of a separate variable in which we contrast that specific category to the reference category that we chose. So in this case, we chose to have the first category, category 1, as our reference. And for each subsequent category, we have a separate variable. So we will get a separate regression coefficient. That means that we'll have 5 different dummy variables. And in this table, we can see which dummy variable represents which category. So what we can see, category 1, we chose as our reference, hasn't been represented in any of the dummy variables, which is correct because we want that to act as our reference category. The second category has been represented in the first dummy variable, and the third in the second, and the fourth in the third, etc., etc., etc. Now, if you want to have more information on this, I'll make another video about dummy variables in which I'll go more in depth about what these actually are. But for now, it's important to know that when you are using categorical variables, you have to always tell that SPSS that it has to take those as dummy variables. And actually, in linear regression, you have to do a similar thing, but then you have to code the dummies yourself because this function is not available in linear regression. Okay, we're going to skip over the tables here in block 0, and we're going straight to block 1, in which we will be greeted once again with our omnibus test for model coefficients. So once again, here we can see the log likelihood ratio, which is very strongly significant in this case. We can also see that we have not 1, but 5 degrees of freedom in this case, and that is because we have estimated 5 parameters. Once again, like I said, we have 6 categories for which we estimated 5 dummy variables, making that there are 5 degrees of freedom. We see the model summary with our -2 log likelihood for this new model with the independent variables included, the classification table, which I will get to in the next video, and we have the variables in the equation. Once again, the interpretation is mostly the same, but in this case we have multiple regression coefficients. So once again, we have our constant on the bottom, we have regression coefficient number 1, number 2, 3, 4, and 5. Now remember, the constant was the estimated value, the estimated log odds on a infarction for the group coded as the lowest. So in this case, our first category, which was the lowest BMI group. So the estimated log odds for the people with the lowest BMI has been estimated to be -1.118. We can exponentiate that to get the odds for this particular BMI group. Now, all of these other coefficients show us the estimated difference in log odds between that particular group. So for instance, for this first coefficient, it will be the estimated difference in log odds in an infarction for group 2 in contrast to group 1. All of these coefficients show us the difference between that particular group and the reference category. So the first coefficient shows us the difference between 2 and 1. The second coefficient between 3 and 1, the third coefficient between 4 and 1, and so on and so forth. So for instance, the fourth coefficient shows us that the estimated difference in log odds for group 5 compared to group 1 is 2.086. And then we can of course exponentiate that to see that the odds are 8.050 times greater for group 5 compared to group 1 on getting an infarction, on having an infarction. And of course we can see all the rest. We can see the Wald statistics being computed. We can see the confidence intervals, and it's basically all the same. Now, one more note here before we move on to the continuous variable. This way of analyzing can also help you in judging whether there is a linear relationship between a variable and the outcome variable. Because not just for linear regression, but also for logistic regression, we need to meet the linear relationship assumption in the case of a continuous independent variable. So in this case, what we can see is that On the first coefficient, there is an increase. Then we see for the second, there is an increase as well. For the third, there is an increase as well. So far, it's looking like a linear relationship. The same counts for the coefficient after that. Once again, it's not perfect, of course. These indents are not equally spaced. But then in the last coefficient, we see that there is a decrease. So that does not indicate that there is a linear relationship. So if I were to analyze BMI for real, I would have to analyze it using this categorical or some other type of categorical variable, and I could not use the continuous version of this variable. Now, for educational purposes, I will still do it, but just note that your analysis would probably be invalid if you did that, if you did not meet this linear relation assumption. All right, so for the last analysis, we'll go back to binary logistic regression one more time. We will take out BMI, the categorical version, and we will take out our continuous variable for BMI. All the rest we will keep the same, and we will just run the analysis. Once again, the output that we've covered twice now, I won't go over again. We'll go straight to the variables in the equation, because that interpretation is a bit different now. Because what do we get? Once again, we get our constant. In this case, what does the constant mean? Well, the constant in this case gives us the estimated log odds on an infarction for somebody with a BMI of 0. Now, that is of course a bit of a tricky interpretation because a BMI of 0 or a person with a BMI of 0 does not exist. However, it's a starting point for the regression equation, which still is part of this mathematical model. Now, you could make that interpretation a bit more meaningful if you centered the independent variable, but I won't get into that in this video, but just know that it is a possibility. Now, the regression coefficient, let's get back to the interpretation of linear regression again. The regression coefficient gives us the estimated difference in the outcome for each increase in the independent variable. So in terms of this particular model, what does it show us? Well, it shows us that for each unit of BMI that I increase, my estimated log odds on an infarction increases with 0.177. Now, since we're on a log odds scale, this is an additive interpretation. So for each unit, I increase with this amount. Now, we can, of course, exponentiate that to get a more meaningful interpretation. And as we can see, the exponentiated value is 1.194. This is a odds ratio. How do we interpret that? Well, for each unit of BMI that I increase or somebody increases, the odds on an infarction is increased with a factor 1.194 in this case. So for each unit that increases, I don't add up this 1.194, but it's multiplied by. So it's a multiplicative interpretation. So that's very important. For each unit, it increases with a factor 1.194. And of course, our confidence interval remains the same, the interpretation. And that is, in a nutshell, how you employ a logistic regression in SPSS, how you interpret it. In the next video, we will get into how to judge the quality of a logistic model using, for instance, the classification table that we've passed a couple of times now, but also to other measures of looking at quality. Hopefully, this video was helpful to you, and hopefully see you in the next